Good morning, I am Mr. H. Thank you for joining me for this video where we are looking at equilibrium constants, the calculation of an equilibrium constant given the values of the species that are involved. This will not be your ordinary question because you have some initial and one final value provided. You have a reaction here, iron, divalent iron, everything here is aqueous, dissolved in a solution. You have divalent iron combining with SCN, thiocyanate, to give you ferrothiocyanate ion. You have to determine the equilibrium constant of this reaction given that you have the initial concentration of iron, the initial concentration of this thiocyanate compound, and the final concentration of your product. How would you go about doing that? This right here represents the equilibrium constant equation that you need to be aware of. For a reaction which looks like this, you see the concentration of the products to their coefficients divided by the concentration of the reactants to their coefficients. You have a product relationship, and then you have a quotient between the products and the reactants. You have to utilize a format or a scheme similar to this to determine this value, your equilibrium constant, which is what we don't have. How would you go about doing it? Remember, the way you determine your equilibrium constant depends on the values of these concentrations, but these must be their equilibrium concentrations. You cannot be using initial or final concentration, you have to be using equilibrium concentrations. In some instance, the final and or initial may be equal to your equilibrium concentrations, but you have to determine that to be the case first before you utilize any such assumptions. How would you determine those equilibrium concentrations of these three items? Well, you'll generate a little table: start, change, and final. We know iron is starting here with a 0.0015. Remember, it's initial, that's final. We know thiocyanate is 0.00085, and we know this has a final concentration, but we do know it started out with 0 because when the reaction started there was none of this. Then slowly it started forming. We know you're decreasing this by a certain amount, decreasing this by a certain amount, because these will combine to form this, and we know at the end the final amounts are provided for this only. It's 0.000175. We don't know what this is. This will be 0.00085 minus x. We know this right here will be 0.0015 minus x. If you can determine x, you're good. Here we know the final concentration here for this specific reaction will represent the equilibrium concentration for your product. You know here x is equal to 0.000175. This is equal to that. You can plug this value right here in places of x, and you can easily determine those final concentrations. For this thiocyanate, you'll have 0.00085 minus that 0.000175. You have a very small value. Let's put it out here. You have 0.000675. That's everything here in terms of molarity, moles per liter. You will do the same thing right here. 0.0015 minus that x value, 0.000175. I get here a pretty small value, not as small as that. It's 0.001325. So we've determined these items. All these items have to do now is end up in the equilibrium constant equation for this specific reaction. And what is that equation going to be? We know here KEQ will be equal to the concentration of that product, which right here is this 0.000175 divided by the product of the final concentrations of these. The final concentrations in this case will represent your equilibrium concentration. You'll do the product of these two. You'll have 0.001325 multiplied by this 0.000675. All you have to do is this specific computation and you'll have your equilibrium constant determined. Let's work in the denominator first. 0.001325 times 0.000675. I have this value which I'm going to save. I'll take the numerator value and divide it by that saved value. I have 195.66, which I'm going to round up to 196, or I'm going to say 1.96 times 10 to the 2. There's no units you want to use for a KEQ, equilibrium constant. You just keep it like that as a constant number. Since this value is a positive value, a large value, it tells you that everything here is going to proceed in this direction because this reaction is favorable. The formation of that complex is a favorable reaction, and you can see that by a high equilibrium constant value. And that's all we're showing you here in this video. Thank you for watching.